Okay, let's continue the lecture. So last time we talked about how to exploit a buffer overflow problem. So to do that, we need to accomplish two tasks. So here is an overview of the memory layout. So this is the stack. And here is the stack. This is the bad file. So the bad file will be copied into memory and starting from the buffer here and upwards. Okay, so the first task, the task A, is to find the offset from the buffer to the return address. So when we know this offset, we can put the new return address to the proper location. So when the buffer is copied to the target buffer, to the destination, it's going to override the return address. So the second task, or the task B, is to find the address of the malicious code or the shell code. So this is our input, right? In our input, we have the new address to override the return address. We also have the shell code. So when the input is copied into the process, right? So the target process. So the shell code will appear on the stack. We need to know the exact address, right? So the exact address of the shell code. So in order to set our return address to point to the shell code. So when the function returns, so it will jump into the shell code for continued execution. So we have mentioned that there are three methods to find the offset. The first one is to use GDB. The second one is to use a no pattern input. So when you have an input with patterns, so when the exception happens, you know what's being loaded into the EIP register. Now you get the offset between EIP and the start of the buffer, because we know the buffer starts with 01, 02, 03, and 04. Right? So it will continuously fill in the space between the buffer and the return address. Now we also know the return address. Here, in this case, will be 25, 26, 27, 28. So we know the offset from the buffer. So here is the starting of buffer. Here is the starting address of return ADR on the stack. So now by subtracting the starting of buffer 01 from the starting of the EIP, we get the offset. Okay, so we can easily get the EIP by reading from the call dump. So this method is actually a little bit better than the GDB method, because when you load something with the GDB or on the GDB, so the GDB will actually push something to the top of the stack. So your whole stack, compared to running without a GDB, will actually be pushed down a little bit. Okay. So the third method is by reading from the disassembly of the code. So we have demonstrated this, and we also have a project for this part. So the second task is to locate the buffer or the shell code, right? So we don't care about buffer the shellcode is our target. Okay, so when address-based layout randomization is disabled, programs are always loaded at the same location. So this is why in the early days, so the exploiting buffer overflows are actually pretty easy, right? So because the program will always be loaded at the same location. So if we use a program similar to the target, we can print the frame address. So for example, we can just add a line of printf in the vulnerable function. So because the buffer sits on the stack, right? So the buffer sits on the stack. So if we don't change the stack layout, by adding this line of code here, it will not change the address of the buffer, right? So the line we add here will only change the code section, right? But it will not change the stack, the stack layout. So by adding this line, we can just print out your target buffer. Okay, so we can take a quick look. Okay, so we already let's disable the randomization. Okay, let's go to lab overflow. Okay. If we look at the source code stack.c, we actually add a line of print here. So we print the buffer address, right? So you can do the same to your project. So if we run stack, okay, so it will give a buffer address. That will be BFF118. Okay, so this is the first method. So the second method to locate the buffer is to obtain from the call dump file. Right? So a call file is the memory dump, the dump of the memory when an exception happens. So it includes everything, and also including the registers. Right? So this included the ESP, for example, EBP, EIP, and also the general registers, such as EBX, EAX, those general registers. So the question is, in the dump call file, right? So which registers content can be trusted? So apparently, so the EIP cannot be trusted, right? Because it has been overwritten. And also the EBP has been overwritten. Right, so let's look at the memory layout. So we have parameters here, say str, we have the ADDR here, we have the old EBP here. So when you return from the function, right, so the EBP, the old EBP will be loaded into the EBP register. Then the return address will be loaded into the EIP register. So when this happens, your program will continue execution under the compromised return address. So this will cause an exception. But at the same time, when this happens, So your ESP actually always points to the valid location, because the ESP, every time when you pop or when you return, you add a 4 to ESP, right? Okay, so the ESP will still point to the valid location. So if we look at this, right, so the ESP will be the address of your parameter. So you can subtract an offset to get the address of the buffer. Okay, let's give this method a try. So here, let's set the ulimit. So this will enable the call dump. Okay, let's run sstack. So this will generate a call file. So again, the buffer is at 118. So let's do gdb stack call. So let's list the info registers. So for EBP, so the register contains 24, 23, 22, and 21. Apparently, this has been overwritten. So for EIP, this is 28, 26, 27, 26, and 25, right? This has also been overwritten. But the ESP, it still points to the stack. We can get the memory content of the ESP, right? So this is, if you look at this number, this is actually right after the EIP. So the location of the buffer will be let's do $ESP minus 0x29 28. So this will give us BFF118. This is the same as what we get from the printf, right? So these two methods, they actually match. Let's quit. Okay, so let's go back to the lecture. Okay, now we have these two methods, right? So we know the buffer address. So we know the buffer address. So here is the buffer address. It's at the BFFF118. So now we also know the offset of the return address. That will be 0x24. Now we can decide where to put our shellcode. Right? Okay, so to make this task easier, we can use something called a loop sled. So the loop sled is basically the technique to put a number of loop instructions before your malicious code. So the loop instruction does nothing. It's just an instruction. It can be executed by the processor. Whenever this instruction is being executed, the processor will move to the next instruction. Okay, so by doing so, our return address can point to anywhere in this loop sled. Right, we can point our return address to anywhere within this loop sled. So this gives you a little bit of flexibility, right? So you don't have to know the exact address of the malicious code. So this could be very useful in some cases. For example, to defeat the address space layout randomization. Like this is especially popular in an attack technique called a heap spray attack. So in the heap spray attack, so you spray the heap, or you allocate a lot of copies of the memory, and in each memory, you put a piece of malicious code. Here is a very long loop sled, followed by the shellcode. So your heap, so assume this is your heap, will contain a lot of copies of such malicious code. Okay? So you also know the rough location of the heap, right? So if you try to point into the middle of the heap, you know the rough location of the heap. Then you can try to randomly point into the middle of the heap. Now, because the loop sled is very large compared to the actual shellcode, so the probability of hitting the shellcode is actually very large. So because you have a large portion of the loop instructions in the heap spray attack, okay? So loop sled can help us to defeat the address space layout randomization. But it can also help us in this case by setting the loop sled before the shellcode. So we can have a little bit of flexibility in changing our return addresses. Okay, here is the structure of the byte file. So we can just do a number of loops, then this will be the return address. Then a number of loop instruction again, and the shellcode. So we can point our return address anywhere after it, right? So here. This will give you a successful shellcode execution. So you can also say add an instruction, say jump instruction, say jump before the return address. Now you can also point to here, here, or here, right? So for example, when you point a return address to this loop instruction, it will continue its execution. It will continue its execution here, here, here. Then there will be a jump instruction going next to the next instruction, loop instruction, to the return address. Then it will continue execution until it hits the shellcode here. Right, so this is the structure of the byte file. So to construct the byte file, you need to fill in two places. So the one is the offset of the return address. We figure out from the task A, right? So this is from task A. Then the second is the approximate location of the shellcode. This one we figure out in task B, right? So next we're going to talk about the shellcode. But before talk about shellcode, we need to talk about something called a string copy hazard. So if you still remember, in the vulnerable function, it uses string copy to copy the malicious code into the destination buffer, right? So string copy, assume a string is terminated by 0 byte. So whenever string copy finds a 0 byte, it's going to stop copying, right? So the string copy will stop copying the rest of the input if it met a 0 byte. So this means that your shellcode cannot contain 0 bytes. Right? So let's go back here. Right? So it means that this part, your shellcode, it means that anything in this block cannot contain 0, right? Not in your shellcode, and also not in your return address, right? Not in your return address. So here is the question, right? So what if your return address happens to contain a 0 byte? Right? So what if your return address happen to contain a 0 byte? Okay. So one thing you can do is to leverage the loop sled. So if it points to here has a 0, you can point to somewhere else. Then it will not have 0 byte. So this is one of the adjustments that you can do with the loop sled. Right? So this is why loop sled is useful. Here we'll give an example, right? So your shellcode actually contains 1 0 byte. Now this will be the last 2 hexadecimal numbers. Okay, so you can add 1 or 2 to this address. Because of the loop sled, we will still execute the shellcode. Okay, so here is a demo. Let's take a quick look. Let's take a quick look. Let's run the exploit. So this will generate the bad file, right? So if we look at this here, those are all the loop instructions. So in x86, a loop instruction is a single byte over 90. So here we set the return address. Okay, then this will be the return address. So here, starting from here, will be the shellcode. So the shellcode is actually very simple, right? So it only contains how many bytes? 16. I think it's 24 bytes. Okay, so the shellcode is only 24 bytes here. So we're going to talk about the shellcode later. Let's try to execute the stack. So here, you see we get the shell promote. Right? So it means that we're actually executing in the shell. So by giving the vulnerable program this input, we actually spawn a shell. So we can type any program like ps, like htop. Okay, so we don't have htop installed. Let's say ls. Okay. Okay, so let's skip this slide. Okay, so let's talk about the shellcode. So the shellcode is the malicious code used by attacker to gain control of the system, right? So it's named as shellcode because originally a shellcode will spawn a shell, but it can actually do anything necessary. Okay, so here is an example, right? So to write a shellcode, sometimes you can just write a simple C program, then you can compile it into .o, then you can do the disassembly. So this will give you some assembly instructions you can use in your shellcode, right? So here is an example, right? So we have the execute. So it's going to call the execute to create a new process. So execute takes two parameters. So the first is the command name. Then you have an array of arguments. So the first argument is the command name. Then the last one will be a null pointer. Okay. So we also have an environment pointer. But you don't have to set this. You just need to put a 0 here. But the question is, right? So if we look at this, the null pointer is actually a 0 byte, right? A 0. So it seems this shellcode needs to contain 0 bytes. But how can we solve this problem? So in the shellcode, usually you are going to use a system call. So in the Linux system call, here is how the system call is being dispatched in Linux environment, right? So here is a user process called the fork function. So the fork, well, it's actually a function in library C. So eventually, it's going to issue a system call. So in this case, it will be using the int_AD instruction. So the int instruction is a software interrupt. So the hardware interrupts can be software interrupt or hardware interrupt. So the hardware interrupt is triggered by hardware. For example, if you receive a network packet, this will trigger an interrupt. But the software interrupt can be issued by your program, usually to access the system call. So in the computer, there is something called the IDT, or interrupt descriptor table. So in the IDT, there is an entry for every source of interrupt. For example, in the 0x80, this will be the system call handler. So for the first entry, it will be divided by 0 handler. Right? There is also a page fault handler. So the syscall handler will save the states to the kernel stack and call the syscall table. So the syscall table is also a table, right? So for each syscall, it has a syscall number and also a number of parameters. So the parameters usually are passed from the user space to the kernel space in registers. So if you have more parameters than the number of registers, you can pass them also on the stack, right? So the kernel space, so the kernel and the user space has different stack. So they have the kernel stack. So this is the kernel stack. So here is the user stack. Right? When you run it in the kernel, it accesses the kernel stack. When you run it in the user space, it uses the user stack. Okay, but the kernel can also access the user stack, right? Because of the ESP register. So when you enter in the kernel, so the ESP register will point to the top of the user stack. By reading from the ESP register, right? So the kernel can access the user stack. So again, so the parameters can be passed in the registers or the stack. So the syscall table is a table of syscall handler. So for the fork, okay, fork has a syscall number of 2, right? So in the second entry of the syscall table, it's going to call the sysfork function. So this is the syscall handler for fork. Okay. So the shellcode, usually it's a piece of machine instructions to launch the shell. So we can use execute bin sh argument 0 to spawn shell. Right here is the register being used. In the EAX, it contains the syscall number. So again, if you look at this, right, every syscall has a syscall number. Then, so the first address will be the command line, which command to be executed. So this is passed in the EBX register. So the second command is passed in the ECX register. So the ECX register contains the address of the argument array. So the argument array has 2 entries. So the first is the address of the command line. So the second will be 0. Basically, it means that there is no more arguments. So if we execute a command in the shell, right? So for example, if we do ls say -l, so we actually have 2 arguments. The first one is ls. The second argument will be -l. Then the last entry will be a 0, right? So it means no more arguments. In the EDX, we push 0. It means no environmental variables. Then we can use int 80. It's a software interrupt to execute the system call. So there also we can use a syscall instruction. Right, so they basically serve the similar purpose. Okay, here is the shell code, right? So on this side, it's the binary, right? So because the shell code is a piece of code, right? So it must be some binary. So here we have the disassembly instruction. It's the same as this binary, right? When you assemble assemble file using a command like NASM, it will turn this assembly instruction into this binary, right? So here, this is so if you look at this, right? So we're actually using this method to combine smaller strings into a larger string, right? So this is actually being supported by the C compiler, right? So if you have 2 strings together so the compiler will actually combine them together into a bigger string. Okay, so don't don't be surprised to see this kind of syntax. It's actually supported by the standard C. Okay, so the first instruction is XOR EAX. So when you XOR something to itself, you actually set EAX to 0, right? So let's draw the figure here. So now EAX is 0. Then we have the let's draw the stack here. So this is the stack. So here is say ESP, your current ESP, right? We push EAX, so we get 0 here. So your ESP also moves down. Then we push this number here, push these two numbers. So this is actually the encoding of //sh and bin, right? So those are the two strings on the stack. Okay, after this, the ESP points to here. So now we move ESP to EBX. So this will be in the EBX. So this will be in the EBX. Okay. Then we push EAX to the stack. This will be 0. Then we push EBX. Again, EBX is actually the address of this string, right? Then we move ESP to ECX. Now here is the ESP now. So move so here, so the ECX will actually point to here. So this is the EBX. So here, this is the ECX. Okay. Okay, here is your current ESP. Every time when you push something to the stack, so the ESP will move down, right? Then we do the CDQ. So the CDQ will actually set EDX to 0. So EDX to be 0. Now at the beginning, we have EAX to be 0. Okay. Then we move 0xb to AL. So now, what is AL? So the AL is actually a historical structure for x86 architecture. So in the early days, right? So x86 is a 16-bit architecture. So every register is 16 bits. So the AX register is actually divided into something called AL and AH. So AL is the lower bit, AH is the higher bit. So later, they extended this x86 architecture into a 32-bit architecture. So now we have EAX or extended AX. But you can still use AL to access this part of the register. Now, at the beginning, we set EAX to 0, right? So EX to be 0. Now here we move 0B to the AL. Now we have a EAX register equals to 0x0B. Okay, so the reason we need to set the EAX register in 2 steps is to avoid 0 bytes in the shellcode. Right, so if you want to set, say, move 0xb into EAX, so in the binary encoding of this instruction, so the 0xb will actually be encoded as 000000B, right? So we are going to have 3 bytes of zeros. So we cannot use this instruction directly. Instead, we need to first set EAX to 0, then we set the lower byte of the EAX register. Then we can use the int 80 to issue the system call. Right, so let's go back to the previous slide. We have mentioned, right, so the EAX needs to contain the syscall number, which is 0B. Right, look at this. So EX is 0B. For EBX will be the address to /bin/sh. This is a string, the command line. So the EBX. So here is the EBX. So here is the EBX, right? So the EBX actually points to the string on the stack. So the ECX will be the address of the argument array. So the ECX points to here on the stack. So points to this block on the stack. If we look at this block, right? So the first entry is the address of the command string. So the second entry will be 0. For EDX, we set this to be 0. Then, so the last instruction will be int 80. Okay, so the key to understand this piece of shellcode is to understand that when you push something to the stack, right? When you push something to the stack, so your ESP always points to this memory location. So if you push the string to the stack, right? So it's actually, so the ESP will contain the address of the string, right? Okay. So here is what happens in the at the runtime, right? So we're not going to getting into details because we have already talked about this in the previous slides. Okay, so let's take a quick look at the shellcode. Okay, so we can actually, let's say micro call, oops. Shellcode.c. So if we look at this, right, so we have the shellcode here. Then we can actually copy this code into the buffer on the stack. So the shellcode here is on the data section, right? So we can copy it to the stack. Then we can actually execute the stack, right? So this is a conversion, a forced conversion of the buffer into a function pointer. Then we can call this function pointer, right? So here we have already, let's say, call shell. Okay, so we can compile this with the -o, say disable the stack protector and also enable the executable stack, right? Let's do the call. See here, we actually get the shell, right? Okay, so let's stop here today.